Thanks everyone for joining. Thanks to both our speakers. It's a very exciting and last webinar that we get before the official workshop, which I want to mention that the registration are now open. So please do go and register for the workshop next month. And I see Jay beat me to it and already put in the chat the link. And so I'm very excited to start to introduce Tom Augsburger. Hopefully I didn't do that too bad. He's a software engineer working on the planetary computer. He's a maintainer of several open source Python library. And for the last few years, he has worked on the Pangeo project. And he's going to be talking some more about the data analysis component of Reanalysis. So Tom, please take it away. And thanks a lot for presenting today.
Alrighty, thank you. Thank you very much. And thanks for having me out here. So cloud native geospatial is kind of the overall theme for today. I'm actually going to bring back the window here, so if you have questions, I can see them. So let me know if you have any questions. But anyway, as we go through this, so just briefly about me, because I think it's kind of relevant. My current titles like geospatial infrastructure engineer. Previously a data scientist, before that an economist, so there's no geospatial here, no geoscience or anything like that. This talk's going to be a bit different from the other ones in this series, which hopefully will still be interesting. Like, I've enjoyed trying to absorb the other talks, but there won't be any integrals or differential equations in this one. I'm also kind of representing two groups today, so I work at Microsoft on this planetary computer project, which we'll be talking about. They run a commercial cloud, which we think is useful for geospatial data analysis. But I'm also a member of the Pangeo community, which is this group of people trying to do geoscience at scale, mostly, not entirely, but mostly on the cloud. So those are kind of the two hats that I'm wearing today, as we go through this. And I'll be jumping back and forth, and I'll try and make it clear when I'm kind of talking for each group. And as for you, I've tried to make it fairly general. If you're a producer of geospatial data, one of these reanalysis data sets, your consumers of that data might be interested in consuming it on the cloud. So what does that mean for how you distribute the data, things like that? Or perhaps you're just interested in the analysis of geospatial data, and maybe you're currently working on the cloud and wondering how you could better use it, or perhaps you're curious about what could be done on the cloud for the analysis of geospatial data. So hopefully keeping things pretty broad, pretty general. Very briefly going to talk through what the planetary computer is, but I'll keep it super short and we'll get to actual examples in just a bit. So first and foremost, it's a data catalog. So we have lots and lots of geospatial data in Azure ready for anybody to use. So, we don't really think it makes sense for like company A and research group B and government agency C to like all have their own copies of public data sets like Sentinel-2. That's like 15 or 20 petabytes. Like, that's a lot of data, but kind of more importantly, it's like a lot of effort to maintain these pipelines to get data from the source, Copernicus in this case, to a cloud, Azure, in a nice, cloud optimized format, and just to keep that pipeline, to get it up and running, and then to keep it running is a lot of effort, and it doesn't really make sense for multiple groups to be doing that if all the data is going to be ending up in the same place anyway. So we're taking on that effort to get data from these providers like USGS, Copernicus, getting these data sets to Azure in cloud optimized formats that anybody can use, ideally use from Azure. In terms of the types of data that we're making available, so mostly public sector data sets. We have lots of remote sensing data sets, so Sentinel-2, Landsat 8, Collection 2, Level 2, NAPE, GOES, so a whole bunch of remote sensing data sets imagery data sets, and then like derived data sets like land use, land cover maps, biomass, things like that. We have tabular data sets, so it's not just satellite imagery. We have things like GBIF, which records observations of living species, made available as a tabular data set. We've got like Earth systems, climate model outputs, so things like this downscaling, CMIP6 downscaling project from the Climate Impact Lab. Another next GDDP CMIP6 downscaling, Terra Climate, GridMet, so lots of these kind of Earth systems data sets, and reanalysis data sets. So we have some of ARO5, not the full catalog yet, but maybe someday. So that's all the data, made available in Azure. And then we have APIs. So getting the data to Azure is like a lot of work. It's very valuable, but it's not really enough, especially for folks working with those remote sensing data sets. We talk about things like Stack and the remote sensing. People get very excited. Their data sets tend to be a bit less structured than these like NetCDF style data sets. So we won't talk too much about the APIs. We'll see them, but won't be a real big focus for today. And then finally, compute. Like that's the big thing is being able to compute on the data within Azure. So very shortly, like that's the idea behind the planetary computer is geospatial data plus APIs and compute. All with like this sustainability focus. Don't know if I mentioned it, but the Planetary Computer team is within the Microsoft Environmental Sustainability Organization. Okay, so I want to focus in on a specific component of like the data analysis lifecycle workflow type thing, and that's on just accessing the data. One of the principles of this whole cloud native geospatial thing is like you have access to all of the data. To put a fine point on it, you have access to all of the data. And like this is, both a blessing and a curse. It's like, you have all these new opportunities when you have access to the, 15 petabytes of Sentinel-2 and, whatever, all these other data sets, like 40, 50 petabytes is our current size of our catalog. And it's like, that's great, but like what do you do? How do you actually work with that much data? Kind of the traditional mode or the download model, where you have some local laptop or in workstation or maybe in like an HPC system on one end, and you're hitting some web server for its data. You request some bytes and it gives it back to you, and you download it like locally. So you make your own local copy. And like that works great for smaller data sets in the gigabytes, terabytes range. But once you're into like the multiple petabytes range, like this just doesn't work. Like I don't have hard drives that could store 15 petabytes of data. Even if I did, my home internet connection is not going to be happy with trying to take all that down. And it breaks down on the other side too. Is like most systems can't handle like shoving that much data up over the internet. So that's kind of this download model is like what we try to move away from when we're working with these really large data sets at scale. And if you're not, like that's totally fine, because as we'll see, like people will say, what do you do when you can't download the data? Like, how do you actually work with it? You just move the compute to the data. You just move the compute to the data, but it's like, how do you actually do that? That's kind of been a question that the Pangeo community has been struggling with, working on maybe for the last few years, 4 or 5 years now. So like I said, it's a community of geoscience people. I would definitely recommend checking out their discourse if you're interested in working on geospatial data sets on the cloud. It's just a great community who have been really tackling this problem from end to end. And so that's what I want to actually go through is kind of a demo of a end-to-end, hopefully somewhat realistic, not super complicated workflow and we'll see what breaks basically. Let me jump over here. So hopefully you can see my notebook now. Just interrupt if it's not big enough, the text, but I'll be talking through things and we'll be able to see the images. So like I said, we're going to avoid this download model. We don't want to try and like replicate all of this data locally. So first thing you need to do is move your compute to the data. So our data is in Azure, and specifically in the West Europe region. So how do we get compute in the West Europe region too? So there's lots and lots of different ways to do that. One of the things that Pangeo has kind of been big champions of is the idea of scalable Jupyter hubs deployed in the cloud next to data. So if you go to planetarycomputer.microsoft.com/compute, you get dropped into this, log in, and you're dropped into this environment here where you choose your environment, click a button to hit start, and we've successfully moved the compute to the data. So this is using Jupyter Hub in the background. It's a real nice way to get these kind of remote kernels, getting, in this case, Python or R or QGIS or whatever, get this compute in the region that you want it, running in the cloud. And then you have your kind of local client. So my web browser here running on my laptop is outside of Azure, but that's okay. I'm just going to be bringing back small results like images. All the heavy compute is going to be happening in Azure. If you're interested, like the point is like you really shouldn't have to worry too much about like how exactly that happens. I really don't want like climate scientists worrying about Kubernetes or things like that, but we are using Kubernetes and these cloud native things like Helm to get the Kubernetes set up, but ideally like you don't have to worry about that. Just to kind of illustrate the point of what does, is it actually important to move the compute to the data, like a very informal benchmark of running GDAL info on this cloud optimized GeoTIFF. So I ran that at my home in Des Moines, time this, give it the URL to the file in blob storage, and throw away the results. So it's only like a few kilobytes of text that's actually returned. I ran that in Des Moines, and we spent 7 seconds waiting for this few bits of kilobytes of data to be returned back to me. If I run that here in my notebook, which is running in Azure, we're down to like less than 200 milliseconds or so, so like 35x speed up or whatever that is, just by moving the compute to the data. So that's like it's been a lot of work to get to this point, but like just a quick little demonstration of the importance of moving the compute to the data. The other thing that we get from the sub, like these geospatial, these geospatial data sets, they tend to be pretty large, right? Depending on the data set, they can be larger or smaller. So it does benefit to work with these data sets in parallel. But that said, like distributed computing is a real challenge. And again, it's like another thing, like ideally, you shouldn't have to worry about it, but we're not to that point yet where you can just like, not worry at all about how your computation is distributed. But one thing that is, a bit better now, a bit easier to work with is we have these libraries like DAS Gateway, which make it relatively easy to do like the infrastructure component of distributed computing. So with this cell here, I was able to create this cluster, which does some work in the background, connect to it, and then scale it. I didn't have to worry about anything like setting up virtual machines or Kubernetes things again, or how they talk to each other, or software environments, or things like that. With this kind of Jupyter Hub type setup, we're able to configure things so that users can just ask for their cluster, maybe customize it slightly, like the memory ratio to CPU, memory to CPU ratio, and then ask for their workers. And then from there, they're just, they're off to the races. So this kind of infrastructure side is I think, easier than ever. And again, that's like a whatever, it's a trope or whatever, but the cloud is like elastic, scalable, things like that. So it's relatively easy to get resources spun up and spun down, and especially easy with libraries like Dask Gateway. So anyway, we have a cluster. We'll be using it in a little bit. Next thing I wanted to talk through is around like file formats. So geospatial data analysis, it does benefit from all these the cloud, all the resources that the cloud brings to bear, but it's not without its challenges actually getting there. Especially so in the climate sciences, libraries like NetCDF are very popular, and so the APIs and the performance characteristics of these cloud file systems like Amazon's S3, Google Cloud Storage, Azure Blob Storage, I think Cloudflare has one too. Like these are very, they have very different performance characteristics. So this thing of just move the compute to the data. Well, we've done that. We have compute next to the data, but we have this huge like ecosystem of libraries that we're very fortunate to have. In Python and other languages as well. We're very fortunate to have these data sets, but like they were built around this idea of a POSIX file system, local file system. So it's going to be quite, we can't necessarily just expect it to just work when we completely swap out the file system. There's not like a single server anywhere. It's a very complicated service that is making these, all of this, 50 petabytes of data available to us. There's a question in the chat, like what's the price of the cluster that I just spun up there? So one of the cool things is that we're using low priority cores for these workers, preemptible nodes. So all the clouds have this idea of like nodes that are cheaper, like quite a bit, dramatically cheaper, but you kind of run the risk of the cloud saying, oh, I need these cores, somebody else is willing to pay more for them now, I'm going to take them away from you. Which is absolutely perfect for these types of data sets, right? Or this type of like interactive analysis, like if 10, 20 of my cores get preempted, like that's totally fine, and I can ask for additional ones shortly later. So next we'll use the Stack API to search for some data. Like I said, this is very exciting for remote sensing folks. It's less exciting for us. I forgot to import some libraries, so I'll run that cell too. And we'll load up some NetCDF, or the metadata for some NetCDF files from this NASA Next GDDP CMIP6 file. We're doing some querying here, so I only want like these 50, 51 years, and only from this modeling center, Access CM2. But anyway, we do this stack stuff to get some links to a file in blob storage. So we have this NetCDF file. If we were following the download model, we would like locally download it to, it would still be in the cloud, but we would locally download it to the hard drive that I'm connected to here. But we're going to try and avoid that. We're going to try and load the data directly into memory. But that's not like exactly straightforward. Like if we just pass that URL to Xarray, it hands it off to like libnetcdf, and it doesn't know what to do with that, HTTP URL. It's like it's looking for a local file or data or things like that. So like we have all this software that's kind of built around this idea of local files, things like that. And it's not necessarily going to work out of the box with these remote file systems like S3 or Azure Blob Storage. And that's a lot of what Pangeo has been kind of working on for the last few years, is like how should we approach this problem? How should we enable geospatial data analysis on the cloud? So taking a few approaches. So there are other file formats like ZAR and TileDB that are cloud native, cloud friendly, things like that. That's like a big ask to get an agency like USGS or NASA to like completely change how they distribute their files, especially when they absolutely have users, customers of their data that want the data in NetCDF, because like that's what they're used to, and it works perfectly fine for their use case. And so we definitely need to like make it clear that if we're going down this route of like converting data or whatever, it has to be worth it. It's not without its costs. A few other, like we're working on libraries within that software stack of like getting data, bytes from some remote file system to higher level libraries like Xarray involves, a few 4 or 5 different libraries, including libraries like FSspec that kind of provide remote access to files. So kind of just showing that here is we can, use FSspec to open up that URL and get this kind of fake file-like thing. It's not actually a real file on disk, but it looks enough like one to trick Xarray and H5netCDF and libnetCDF into thinking it's real enough that we can actually read the metadata is all we've read in here. But notice that took like a second and a half to load just the metadata. So we haven't actually loaded the precipitation values here. That's still out there in blob storage. We haven't pulled that down locally. So that's like a little painful for a single file. And if we try and do that for all, it's like 8 or 9 assets in this stack item, it's like 5 seconds to load. Again, just a bit of metadata. We still haven't loaded any data yet. It's still lazily loaded. So, that's like not great, especially for these interactive workloads at scale. So what we're doing is like exploring these alternative file formats. So like ZAR. So in this case, we have this GPM iMerge data set, and in 2-3 seconds we can load up all the metadata. Again, still haven't touched files, but load up all the metadata for this 17 terabytes here, 8 terabytes here. So we have this really large data set, large time series, spatial extent, that we can load all the metadata and then go and do our interactive computing. There's these other things I'm going to skip through just for time. There's ideas like these cloud optimized reference systems, kind of similar sort of ideas like leave the data, recognizing we don't necessarily want to host like 2 copies of the data. People want the data in netCDF maybe, so how can we provide cloud optimized access to that data in netCDF? So there's this idea of like per chunk reference file systems. I'm going to skip over that just for time, but that's a thing that we're exploring as well. And I wanted to go through like a semi-realistic example just in a couple of minutes. I think it'll be hopefully interesting. We're going to load up some ERA5 data, specifically the skin temperature or air temperature at 2 meters, that data. And we'll go through and do some computations on it. So ZAR, again, it's never perfect. So ZAR has, you have to have fixed size chunks along time. And this data set is chunked by month, and months are variable length. So it does take a bit of time to load up the data, the metadata, sorry. But once we've got that, we can kind of go and do our workflow. So we can plot the first time step. I'll talk around what's going on over here. I'm actually going to reopen this one because it didn't look like it was running. Put that there. Okay, cool. So we have our skin temperature, and I was searching around what to do with ERA5 data and came across this idea of a climatology. So in Xarray, we're gonna we would write that as group by time of year. So I think I have like 4 or 5 different 4 or 5 years worth of data, and we'll group by the day of year and get the average temperature for that day of year across the 4 or 5 years. So I'll kick off that computation. I'll persist this small result in the cluster. Oh yeah, I forgot to mention, this is what we would like to write. It doesn't quite work today because basically how Xarray uses Dask and how Dask handles communication, it isn't perfect today. It will be in the future once this pull request is merged by Deepak and Anderson. But for now, we're going to kind of use this lower level Flocks library, which implements the kind of intelligent algorithms for doing this kind of group by computation. So anyway, once that data is loaded, or as it's loading here, this is our cluster, it's activity over time. So all of vertically, we have 80 or so cores, and going horizontally, this is like the activity of that core over time. So that's churning through this computation, working on this kind of daily climatology, averaged over 4 or so years. So next thing I came across was like, oh, you need to do like an anomaly. So you take like your timestamp, that timestamp day of year, and subtract the average, the climatology average over 4 years, and then do that. So I was going through that computation. I got it for a single one. It looks, I don't know if it looks good or not. And then I was going to run it on the whole thing using this map blocks to apply that to each block of the function. And I ran that and was taking a look at the output, and I noticed this kind of pretty patterns, like, oh, like this is a nice pattern. It's like we have this kind of day-night cycle here. I was thinking, wait a minute, I'm computing a daily climatology. Why do I have a day-night cycle? That doesn't make any sense, I don't think. Like, again, I'm not a climate scientist, but it's like very struck by this, like that doesn't really make sense. And I think what happened is all the examples I was copying from were working with daily data, but the era 5 data I was working with was hourly. And so I ended up doing this daily climatology or anomaly calculation on hourly data, which I think doesn't make sense. But we're able to correct that. We can ideally do this resample to daily data. So resample from hourly to daily. For now, we'll use the kind of lower level computation. Kick that off. I'm going to skip through that because I'm running out of time. But anyway, the end result is, I think, this hopefully a bit more valid, let's say, computation for the daily anomaly over these 4 or so years animated here. So I might be like, I was very struck by this. It's like I was really obviously new to this, actually computing scientific things, but I was able to pretty quickly code that up, 15, 30 minutes, get that coded up, that mistake coded up, and I was able to quickly get to the point where in my analysis where I recognized that mistake of what are you doing, hourly climatology with daily data? It's like the other way around. It's like, so anyway, I think that might be. I think that's personally interesting is with this kind of interactive analysis at scale, we're able to quickly do these analyses, get these, interpret these results and recognize in this case that, hey, you made a mistake and then correct it. So anyway, that's the basic idea. There's a question, I'll wrap it up now. There's a question, if I'm working, yep, you understood correctly. If you're interrupting, or if you're working interactively, the cloud might come along and say, hey, I need this processor now. And then depending on how things are set up, it could like automatically rescale, ask for more when they become available, or it could just be, you can manually rescale, things like that. And libraries like Dask are flexible enough for workers coming and going, they'll reassign tasks, things like that. So that's the basic idea. Planetarycomputer.microsoft.com if you're interested in learning more about that. Discourse.pangeo.io if you're interested in learning more about Pangeo. Awesome. I did go a bit long, so maybe we have 2 minutes, but if anyone has questions, I'm eager to hear them. Thank you.
Any questions for Tom?
I think there was one question earlier in the chat. It was just a clarification from Gael. What's the price per hour for the instance 80 cores for that you use for this demo?
Yep. So these are the preemptible nodes, so they're pretty cheap. It's going to be like $1 a day, I think. Don't quote me on that, but there's like an Azure pricing calculator that I can put in the chat afterwards. But it's somewhere in the order of dollars a day for that. Again, because we're using those preemptible nodes, that makes the price a lot cheaper.
Okay. And Sergey apparently has a question, but he keeps it for at the end of the hour. So he will keep us guessing. Tom, thank you so much for the presentation. That was very exciting. And then, thank you so much.
Thank you.
Our next speaker is Elizabeth Kent. I believe she's on. Yep, there she is. She's a research scientist at the UK National Oceanography Centre since 1990. Her expertise is in quantification and understanding of long-term change in surface marine parameters important for air-sea exchange of heat and momentum. Her research focuses on quantifying the uncertainty in marine meteorological in situ observation and to develop bias adjustments for systematic error. And she works on the development of gridded data products for air-sea fluxes, and she was also a contributing author for the IPCC, the 5th and the 6th report, the working group one. Elizabeth, please go ahead, and thank you so much for making the time to come and present to our webinar.
I'm going to talk about the role of sea surface temperature forcing in reanalysis and our ability to reconstruct climate records. And I'm focusing on in situ and long-term observations. Okay, so what observations do we have? This shows observations from the first week of December in 1880, sea surface temperature, sea level pressure, air temperature, and cloud cover. So you can see this is pretty sparse, but we have similar coverage for all of the variables. Whizzing forward to 1950, we can see we have quite a bit more data. Particularly, we've now got some observations in the South Pacific, for example, but it's still pretty sparse in some regions. The North Atlantic is really the only place that's really well sampled. 1990 is probably our best sampling. You can see we have pretty good sampling across the Northern Hemisphere in the shipping lanes. Again, you can just start to see differences in the sampling for the different variables. For example, we have fewer air temperature measurements than we do for sea surface temperature. Now, moving on to more recent data, we can see we've really got starting to get a much sparser observing system here. Sea level pressure, in great interest to reanalysis. We can see we've got real data gaps in the tropical Pacific, and sea surface temperature, and is reasonably well observed. We can see the impact of drifting buoys in the Southern Ocean. One thing I'm particularly concerned about is cloud cover. We can see that's really sparse, and only 16% of the ship observations now have cloud cover. So although the observation density for pressure and air temperature look fairly similar, if you zoom in looking at different platform types, you can see that the observation types are very different. You can see that we have sea surface temperature. You can see we have the ship tracks, and those will be transient observations, whereas the observations in, for example, blue and red will be observations from buoys, and we'll have high temporal sampling in those regions. So it's a bit more complicated than just looking at maps. So thinking about near surface temperature variability and air sea fluxes, what's the role of sea surface temperature forcing in reanalysis? So how the data and products used. So for atmospheric reanalyses, the sea surface temperature forms the lower boundary. The product may be modified. For example, if it's a bulk estimate of SST, so subsurface, it might be converted to skin, or it might be perturbed to give an ensemble that captures the likely uncertainties, and we get a range of different instances of the reanalysis. For ocean and coupled reanalysis, the surface temperature will be nudged towards the SST field. It's important to note that long reanalyses may not have a consistent SST record. For something like the long 20th century reanalysis, it actually starts before we have the ability to produce even sort of quasi-global sea surface temperature records. So that relies on the SODA-C sparse reanalysis, moving into using HAD-SST2, but also MERA merges sea surface temperature analysis. So how do we represent variability? You saw the very sparse observations we have. For the modern record, we also have satellite SST. So one way, again, is to use ensembles, and those can represent data uncertainty. So where we have known biases in the data, we can use an ensemble to represent that uncertainty, and also missing variability. Either filling large gaps, for example, as we saw in the tropical Pacific and Southern Oceans, or also getting the statistics right for the subgrid scale variability, which is important for air sea fluxes, for example. So this is a schematic, a fairly well-known schematic showing the temperature variations in the ocean. You can see the cool skin right at the surface, the radiometric skin, and then the subskin temperature is a bit warmer, and then the temperature cools with depth. So on the left, we have a schematic. This is from Ward 2006. And on the right, we can see some real data. So this is a profiler just going down to the top 2 meters. So we can see the skin temperature variation, about 0.5 degrees in this case, and then a larger variation showing the diurnal temperature change. This is from the same paper, we've got a bit more detail here. We've got a few hours of data over the top 5 meters, and we can see we have a very, very distinct diurnal warming layer. If you look at the middle of the time series plots, you can see we've got quite a rapid jump showing the temperature difference across the warm skin. The red shows the warm layer, and the blue shows the cool skin, and the lower panel shows the difference in fluxes. So we have 20 watts per meter squared difference between looking at whether we're looking at the subsurface sea surface temperature or the skin sea surface temperature. This is another look at the same effect. So this shows data from a ship in the North Atlantic, and here we've plotted, the authors have plotted the temperature difference across the cool skin warm layer as a function of wind speed, and you can see several different models that have been used to estimate this difference. So you can see that some of them don't do a very good job of getting that variability, but you'll also see that there's kind of about a degree scatter in the data. And some of that will be observational biases, but these sorts of differences in temperature are critical for getting accurate fluxes, and it's really interesting to think about how reanalysis might represent such variability, and indeed the data products that we have. There's also uncertainty in air-sea exchange parameterizations. If we just focus on the top left panel, this is the drag coefficient, which gives the stress, which is usually thought of as quite well known. These are about 10 different parameterizations, some of which are used in reanalysis. And we can see we have variations in the drag coefficient across all wind speeds, but particularly the high and low wind speeds. Some of these parameterizations are tuned to bulk temperature, some to skin. So if you use, for example, a parameterization that uses skin temperature and you only have bulk temperature, you've also got some added uncertainty in estimating the skin temperature from the bulk. And as we saw in the previous plot, there is a substantial uncertainty associated with that. So this uncertainty will affect the accuracy of air-sea fluxes in single domain analyses, atmospheric or ocean reanalyses, and will also can contribute to the uncertainty in coupled reanalyses, because these difference in the parameterizations will actually affect the transfer between the different domains. So thinking about construction of data products, so this is a paper we did for the OceanObs 2019 conference, where people were thinking about the future of ocean observations over the next decade. This is a rather idealistic look at generating data products, going from generating user requirements, gathering your data together, evaluating, selecting, estimating uncertainty, biases, using ancillary data to estimate uncertainty and evaluate and do the bias adjustment. It envisages a sort of continual loop of improvement. And in this plot, reanalysis is shown as a sort of a customer for this improved data. But it'd be nice to envisage that we could sort of embed this sort of bias adjustment and evaluation within the reanalysis process. So one thing that we worry about are pervasive biases in long-term sea surface temperature. The plots on the right show the warm biases we see in sea surface temperature across many different data products in World War II due to differences in observing practices. And work led by Duo Chan showed that these biases could be attributed to differences in inaccuracies or non-availability of metadata, looking at the different measurement methods, and they were able to substantially reduce this uncertainty. But this information hasn't yet fed through back into the generation of data products. There's quite a long gap between sort of innovation in understanding data and improving the SST products or any data products themselves. Critical to understanding this was looking at diurnal cycles. So we're looking at sort of long-term or sort of errors over many, many months. But what was critical to understanding this is looking at difference in diurnal cycles, because the different types of observations have different diurnal cycles, and that's what's shown in the bottom left there. Again, differences in diurnal cycle are critical for air temperature. The plot on the right shows the estimates of the diurnal heating bias. So basically at night, during the day, ships heat up, and the air temperature that you measure is elevated. We fitted an empirical model to many different ships. Here are 16 examples, the early ships on the top left, and the later, most recent ships on the bottom right. And you can see that each individual ship has a very different characteristic of heating during the day. So we've used constant input. So the input for each for the model is cloud cover, used to estimate the solar radiation and relative wind speed. So to do the bias adjustment, we need environmental information, so cloud cover and wind speed. We need metadata, vessel speed and course, so that we can estimate the relative wind speed over the ship. And this works best for long tracks. So we can see that if we want to use all hours air temperature, for example, to assimilate into reanalysis or to generate products, we're going to really need to understand these rather large differences between different ships. So what are the barriers to doing that? One thing from the International Comprehensive Ocean Atmosphere dataset, which is used for most of these data products, you can see that over time, the availability of ID information varies quite dramatically. There are times when we have almost none, but more recently, most of the ship observations are associated with a known vessel. So using ship tracking, we were able to fill in or cluster together some of these ships, and also join sort of track fragments together. And the success that we did that is shown in this rather lurid plot at the bottom, and the residual untracked data is in yellow. So for reanalysis, the benefits are for per ship bias identification, if that's something that's used. We can do better gridded products with more realistic uncertainty. But the question is what to do with these untracked observations. So one reason why the tracking doesn't work very well, this is some raw data from Monterey Telecoms, which is the early GTS. So you can see that it wasn't all to do with our poor performance of our tracking algorithm. We can see there's lots of problems with location differences, location problems. But we can also use different types of data. If we compare different types of data, we can understand the differences between them. So the GTS data, sometimes we also get the data in delayed mode, and comparing these different versions of the same data source that have gone through different types of data management is really key to understanding biases. One thing that's important, so this is from a similar period, we can see that we've gathered together ship observations from different IDs. So we can see many of them had blank IDs. Some of them had a ship number and some of them had a call sign. And because we can associate these all with the same ship, we can remove off-track observations, but we can also get metadata. We can identify that this is the aircraft carrier Franklin Roosevelt, and we can get information about observational uncertainty. So so this is critical to understanding data quality. One other thing we can do is the platform on the right, was identified as a ship in ICOADS. Many observations in some of the numerical weather prediction data sources have inaccurate platform characteristics, and if you think this is a ship, you will be treating it rather differently to if it's a platform. And you can see that a lot of the tow buoy data are also flagged as ships in ICOADS. So you gave me some exam questions. So thinking about coupling that's feasible by 2030. So I think the outcome here is it's going to be challenging. Resolving and parameterizing the gradients near the ocean surface is going to be really challenging, even for the modern observing era. And I think one question is, can air sea flux parameterizations be tailored to different resolutions? You know, can we actually optimize the parameterization of exchange for depending on the horizontal variability and also the vertical gradients and whether we have skin or bulk temperature. So talking about cataloguing the observational data, I think it's important to consider the need for evaluation as well as assimilation. So there's a focus for sea surface temperature and pressure for reanalysis, but we also need the other variables. So for example, air temperatures and humidities. Some will be assimilated, but we can also produce products for evaluation. Multivariate observations with rich metadata are the most valuable. If you're doing cataloguing, you need to consider the granularity because some archives are extremely heterogeneous. Sampling of the diurnal cycle is critical. It's needed for coupling, for looking at air-sea interaction, and also for identification of solar-related biases. And for that, we need cloud cover. Observations that cannot be automated are declining in coverage. And for example, we have clouds and weather reports. And weather reports could also be important or useful for evaluation in a more qualitative way. And we also need to start to be able to accommodate non-standard observation types with data systems, new data systems, data for evaluation, quality control and metadata. If we're starting to get new observation types in, it's going to be really important we evaluate them, and resources are going to be needed for that. This is an example of some papers from OceanObs. So there's a real wealth of information, some specifically for reanalysis, some for air sea fluxes, and some for variables of interest. So there's a lot of information and recommendations in those papers. Identifying priorities for data rescue and reprocessing. We really need to build a data system for rescued and reprocessed data that retains all of the recorded information. We need to archive data as it's recorded before translation or conversion or correction. As we've seen with issues with the ICOADS archive, which has been assembled over many, many decades, you can really see difficulties that have arisen with problems with translation and inconsistencies. So if we start to archive data as recorded, we can go back and reevaluate when we work out how to do. We can either correct problems or just work out how to do things better. So we really need to evaluate all of the data sources in ICOADS, pre-process the data to correct some of the issues that I've shown, and rebuild the archive. Open source tools for translations, QC, corrections, evaluation and comparisons will be really important. Multivariate data, really important. We want to retain and embed all the documentation, metadata and logbook images. Keep talking about the diurnal cycle. Resolving that is critically important. Sometimes only observations at midday were rescued, which was a disaster. So when we've got marine data, when we've got very sparse data, it's hard to assess the value of it. If we've got a ship traveling through an area where we have no other observations, it's tempting to think that's really important, but it's actually, you know, hard to evaluate the data, and it may be better to focus on data that are in sparse regions, but not very sparse regions. We need to compare the data sources, duplicates where we have the same data with different histories, and also buddies, nearby data from different sources. Really, really important to have rich and varied data. Opportunities for collaboration, talk about joint infrastructure. We really need excellent data provenance if we're going to do observation sharing and diagnostic sharing. We need unique observation identifiers, ideally from data providers, that need to be retained all the way through the data system and the reanalysis and the feedback. Opportunities for shared experimentation. It would be good to have code to allow people to run offline and embedded analysis. assess the value of newly rescued observations. People are trying to justify this, and it's hard to actually sometimes say what was important, what was valuable. Outreach with aligned PhD students and researchers outside reanalysis centres. So have projects designed to answer key questions with help and support from reanalysis centres. And collaboration between reanalysis producers would provide consistent outputs, which would be helpful for data users. So collaboration between climate modelling or data products, the provision of outputs in forms that are really easy to use, monthly means, where we have variables with nonlinear relationships, for example, different sorts of humidity estimates. You know, you have to download data at high resolution to do an accurate comparison, 10-metre values over the ocean, gridded output for direct comparison with data products, monthly and daily means, land and ocean data at 5, 1 and 2 degree resolution, and also regridding tools, variables for height adjustment, and surface exchange at native resolution. So those of you that are familiar with ocean interaction terminology will understand what I'm asking for there. So basically you could adjust from the output height to any other height. Would it be possible to embed bias adjustments and QC into reanalysis? I think that needs improvements to the solar estimates, but that would be one way. I mean, that's happened for radiosondes. You know, can we actually extend that to do that for surface data? And what about data withholding? And finally, the surface marine perspective. Significant advances. It would be great to use reanalysis output to assess and improve observations and data products. Barriers, a lack of funding and expertise for data evaluation, bias adjustment and uncertainty estimate. Data idiosyncrasies are a huge barrier to wider involvement in data product and also to the use of sophisticated statistical methods. It's also hard to identify sometimes when an observation has been assimilated. You get a list of types, but you know, was it assimilated? Was it thrown out? What way? I know we have feedback, but it's, you know, it's been hard. You know, we need good systems to be able to link everything back together and get that feedback all in one place. I think reanalysis centres and data providers are collaborating quite well for SST and pressure, but perhaps need more closer interaction for other variables. I think we need improvements to the data system, feedback from reanalysis and a continual repeat of that. We need the observations to evaluate reanalyses. Observational data sets, we need multivariate data, and lots of different platform types because they all have complementary sampling and characteristics. And uncertainty. Uncertainty is usually quantified by data comparisons, for example, variograms or three-way collocations. And one of the real barriers is a lack of long-term reference observations. I think I've probably gone a bit over time, but thank you. Thank you for that.
Thank you very much, Elizabeth. Question. Okay. Oh, hang on. Now I see everyone's icon. Shane, I don't know who was first, but I'm going to start with the bottom up. So Shane.
Hello, hi, Elizabeth. Thank you very much for your talk today. I have a quick question, technical maybe, and I'm sorry if you answered it already. So do the current atmospheric reanalysis represent in any way the diurnal cycle of SST or not?
Some don't at all. ERA, I think Dick D was here. ERA does produce a skin temperature, so you do get a surface skin temperature over the ocean, but which involves a skin and a warm layer model. But when I've looked at it, it didn't look actually very different from the sea surface temperature. There may be people here who can answer that better than I can, but certainly if you look at this sea surface temperature in some of the reanalyses, you won't see any diurnal variations.
Yeah, I think I looked at the SST from era 5, and I think even if it's what hourly, they were actually daily values, right? So, all right, thank you.
I mean, that's one thing. It's often, I think, I say one thing that's really improved is the ability to find information for the different reanalyses. You know, for example, again, ERA, the ECMWF wiki pages are just great for actually trying to drill down and find information that a few years ago was almost impossible to find. And one thing that has now improved, but actually, you know, sea surface temperature wasn't included in the outputs because it was a forcing variable, so you had to go somewhere different to try and find that.
Thank you.
Isla?
Thanks for the talk. I think you kind of addressed my question in your last slide, but I was wondering if there's currently any feedbacks to kind of, you know, use reanalyses to detect the kind of issues you find in the observations. You know, if you can see very large analysis increments for certain areas, does that kind of feedback to allow you to detect errors in the observations?
So I've looked at reanalysis feedback, and one of the things I was trying to do, for example, was to identify observations that have been reflected. Sometimes you get the position is in the northern hemisphere instead of the southern hemisphere, and it was actually really it wasn't the only thing you could do that for was pressure. I think the differences between the observations and the reanalysis were so noisy that you couldn't actually do that from the feedback output that we had. I think we're understanding the observations a bit better, and I think it would be really nice to have a dialogue about how we might be able to sort of embed that evaluation into the reanalysis. But it's rather hard to imagine. I think there would have to be a sort of special run to do that. It's kind of rather hard to imagine that sort of happening with the normal sort of runs that you get.
Thank you.
And I think we have just time for one last question, Sergey. I see you have had your hands up for a while. So.
I'll have one question for Elizabeth and one question for Tom. For Elizabeth, so if you think about reconstruction of large-scale SST patterns like El Nino, or corresponding patterns in the Indian Ocean, North Atlantic, how far back in time can we go and still have a reliable reconstruction given existing observational records? What's your scientific judgment?
So the observational data sets that are available go back to 1850 or 1880, and that's I would think more like 1900 to get a. I mean, you can always use the uncertainty. I mean, you can project these large scale modes onto the data we have. So with a large uncertainty, you can, and when it's poorly constrained, you won't know what, you will have a wide range in the ensemble. But I think probably 1900 you'd start to be constraining things. I think 1880 is a bit early. And you've obviously got the issues with data biases in World War II, which also coincided with an ENSO as well. So yeah, I don't know. I mean, I think it depends on the accuracy that you require. I mean, it's one of those chicken and egg things. So I'm not really sure we can answer that, and it depends. I mean, sampling in the Southern Ocean has always been terrible. So if you care about what's going on there, you're going to struggle at any point. But I think we're really starting to understand some of the biases in the data, some of the uncertainties, and I think we will make progress in that area. But I I think you've asked me a very hard question, actually.
No, I think that's yeah. Thank you, Elizabeth, for your excellent slides. I really appreciate the effort you put into answering our questions. So I guess one last question for Tom Augsburger. So I think it's exciting how the cloud providers are trying to facilitate non-profits or private industry and honestly government users access to the data. What do you think is this if as a community between the government agencies and private industry we need to invest into a couple of things that will really make this ecosystem flourish, what are the things would be?
Yeah, I think first answer is yeah, I don't really know. That's definitely outside of my expertise, but we do talk to a lot of groups, either academic, private industry, government agencies, and in between that are thinking about this. One area that comes up a lot is around like climate risk services, which isn't super well specified, but that basic idea of providing these services for analyzing risk to the consumers, or mainly private industries, but even like Microsoft itself, like we have data centers and we care about the risks that they face under different scenarios. So that's like one industry vertical, whatever, that I think is has a lot of interest around it right now. And then we're obviously interested in it because like we think that geospatial data is going to be key to that and the analysis of it. And then the other thing I'll say is just like lots of groups are talking about this, and like groups like CSIRO and others are from Australia are looking into this, specifically like how they can encourage that kind of economic development within their region, again, fueled by this type of geospatial data analysis.
Okay, thank you.
Thank you.
Okay, well, we are over time, so I would like to thank both speakers, and I guess I hope to see you all in a month from now, and we'll be talking some more about the webinars, but also we'll have new speakers and we'll have breakout session, and it's very exciting. So please do remember to register. Sergey, anything else you want to add? No? Okay, well, thank you so much, everyone, and I'll see you soon.